the seminar is about stability, but we saw the notion of flexible stability, which in the long run might be even more important than stability, I must say. And in a way, the first positive results about flexible stability for groups for which stability is not known is the results of Aryeh Levit, Yair Minsky, and Nir Lazarovich about the surface group. And today, Nir Lazarovich is with us, and he will present to us this joint work. Thank you very much, Nir, and the stage is yours.
Okay, so first of all, thank you for the opportunity to present this work. Okay, so yeah, we're going to talk about flexible stability of surface groups. Okay, so the subject is going to be surface groups. And this is joint work with Aryeh and Yair. Okay, so let's get to it. So I remind you I should apologize and say that I do not attend the seminar just because the time difference is too crazy. So I don't know what happened in the last lectures. So,
but that's okay. That's okay. I mean, you can explain more than needed. It's always good.
That's good. So just let me know if I'm repeating too much or something like this. I'll adjust myself. Okay. So yeah. So what's the idea of stability? We all heard about it enough. So here's my slogan for stability. Every almost action is almost an action. Right? So what's the basic idea? You're given some relation, let's say, you want, for example, things to commute. And then you're given two permutations. So I should say all of the stability results I'm going to talk about are stability in permutation groups. Nothing about unitary groups and stuff like this. So you're given two permutations, let's say alpha and beta. And you know that alpha and beta kind of satisfy this relation, meaning that on a large percentage of points, so those are permutations in Sn. So on large percentage of points, this relation is satisfied, and you're asking, can we find alpha prime and beta prime? Again, permutations in Sn, which actually do satisfy this relation. So alpha prime, beta prime is just on the nose identity. And they're close to alpha and beta. So alpha and alpha prime agree on large percentage points. And the same for beta and beta prime. Okay, so this is stability. So for example, you want permutations almost commute. You want them to actually commute by changing a few their action on a few points. So this is actually the case. So this is resolved by Arjantseva and Nesco. Okay, and now maybe this was this relation. Does hold for this relation. What about taking 4 permutations and asking for this relation to hold? Okay, so is it true that if you almost satisfy this relation, you're close to permutations that do satisfy this relation? Okay, so we don't know, right? The answer is we don't know. But so this would be stability of the surface group. Those of you who know, this is the defining relation of a of a surface of genus 2, the pi1 of a surface of genus 2. So we don't know the answer to that. We don't know if it's stable, but we know that it's flexibly stable. So what does it mean to be flexibly stable? It means that we don't look for alpha prime and beta prime in the same permutation group, the same number of elements, n, but we allow ourselves to increase by a tiny bit the amount of points that we are given. Okay, so alpha and beta are defined on n points. Then you add a few points, something that's small relative to n, and you want to find alpha prime and beta prime that actually do satisfy the relation and are close to the alpha and beta that you had before. Okay, so that's the general idea. So now let's go into the definition. So I'm sure you saw the definition of the Hamming distance. So this is exactly this measure of how close permutations are. Say that two permutations, we measure the distance, the Hamming distance of two permutations as the percentage of points on which they disagree. Okay, so the number of points I such that sigma I tau of I distinct, and you want a percentage, so we divide by n. Okay. So this is the Hamming distance, and here is flexible stability. So you probably defined flexible stability for more general groups, but let's focus here on finely presented groups, because soon we're just going to talk about the surface groups, and they have a one relator presentation, right? So even this definition is more than what we need for the statement of the theorem. Let's go over it anyway. So we're given a list of relations, which are just represented as elements in the free group on S1 up to Sk. And we'll say that this presentation is stable. Let's do stable first. If for every epsilon there exists a delta such that for every n, whatever some quantifiers, now let's understand what's written next. So I'm given k permutations in Sm. This is the same as just specifying a homomorphism from the free group to Sm. Okay, and we want it to be an almost action of this group. Okay, so what's an almost action means that all the relations are almost satisfied. Okay, so for each relation, I want the distance from the image, of the image of this relation in the symmetry group from the identity to be small. Okay. And if this is satisfied, so if I have an almost action, I'll say that the group is stable if I can make it into a close by action. Okay, so I can find another map from the free group that now satisfies the relation. So it actually descends to a map from the group, let's maybe give it a name, gamma. Okay, so from gamma to Sn, such that it's close to the previous one. So in the way we said before, this would be almost action. This would be almost an action. Whoa. Okay, so every almost action is almost an action. Are we okay so far? Good. So what is flexible stability? So flexible stability, I just need to add some quantifiers at some point. So for every epsilon there exists a delta such that for every n, so now I can even put the next quantifier right here. So there exists a big N, but big N is not that big. So such that N is between small n and 1 plus epsilon n, such that for every almost action, so this line is just the same, I have, I'm almost an action, but no, the action is to n. Okay, so note that in this formula I'm comparing distances between Sn and S lowercase n and S capital N. But what you should just think is Sn sits inside S. Now I'm okay. Maybe I should change it to another letter. Maybe M. Okay. N is taken. Let's do n prime. Okay. So you should think of Sn sitting inside Sn prime as just the permutation of the first n symbols. Okay. Any questions so far? Good. So now let's think of it more geometrically or combinatorially. So I want the interpretation of this using Schreier graphs. So whenever I'm given an action of a group and a generating set, so this is the same as maybe an action of the free group for our purposes, we can form the Schreier graph of this action. What's the Schreier graph? The vertices are the elements on which you act, so one up to n in our case, and we connect to by a labeled edge, labeled Si, if Si maps X to SIX. Okay, so we connect X to its image under Si. And this gives us a labeled graph. Every vertex has k outgoing edges colored from S1 up to Sk. Okay, and this represents the action for us. So, so now let's try and understand what does it mean to be stable when we look at Schreier graphs. Okay, so the challenge for stability, this almost action, is the same as saying I'm given some Schreier graph of the free group for which I know an extra condition. The extra condition is when I follow the relation as a path on this graph, I, with high probability, return to the same point. Okay, so what do I mean by that? For example, if my relation is the commutator of A and B, and this is the Schreier graph that I get, okay, then I'm starting from some point X, I'm doing A, and then B, and then A inverse, and then B inverse, and I actually ended up in the same place. Okay, so the relation is satisfied for this X. But for some others, it's not satisfied. Okay, so let's maybe pick one for which it's not satisfied. So let's maybe start, say here. Okay, if I do A, B, A inverse, B inverse, I end up somewhere else. Okay, but know that if I repeat doing this commutator, I will at some point end up in the point I started. Okay, so again, the condition for the challenge for stability is that most such paths actually end up where we started. Okay, close up. And now, what does it mean to be stable? Being stable means you can rearrange some edges, so change a few edges. Okay, so what's a few? A few is a small proportion of the edges, so epsilon times n, so that actually all paths close up. Okay, so the analogy I like to think of is you start with something like the German railway system, where it's kind of working locally, but if you want to go from A to B, you're probably going to be stuck at some point, and you change a few railroads, and you end up with a Swiss railroad system where everything works just fine. Okay, so this is what we're after, stability. Okay, and of course, flexible stability just means I'm allowing you to add a few more points and change again a few number of edges so that it works. Okay. Good. So here's the theorem. The theorem says if sigma is a surface, so a closed orientable or hyperbolic surface, then the fundamental group of the surface is flexibly stable. Okay, so that's the theorem we are going to prove. And let me just remark a few things. So we still don't know if it's stable, so whether this flexibly stuff is actually needed there. So this is still open. And let me just say that some of those conditions are really not necessary. So if the surface is not closed, then it's pi1 is free. Okay, so free groups are stable. So I could have stated it without the word closed. And the same for hyperbolic. So if I have an orientable surface, it's either the sphere, the torus, or it's hyperbolic. Right, so the sphere has trivial pi1, the torus has z squared as pi1, and that's exactly the result we started with by Arjantseva and Onescu. Okay, and I guess orientability can also be dropped, but somehow it's not in our proof. Maybe we should write it. Okay, is the theorem clear? Okay. Yeah, let me just add maybe one more thing is that as far as I know, this is maybe the only sort of non-trivial example of a group that's not amenable and flexibly stable, and which is not just a free product of such things. Is that true? I mean, I guess all the experts are here, so.
Yeah, as far as I know, I don't think I know any example which is flexible, stable, and not known to be stable except of this one. By the way, what do you believe? Is it stable or not? I mean, like the proof give you some intuition?
The proof really doesn't, that somehow, I mean, we're seeing where the flexible stability comes into the game. I mean, it's in such like small details that it's hard to separate from whether it's essential or not. So, I don't know. Any more questions? Okay. So yeah, let's go into the proof. So from this point on, it's just going to be the proof of this theorem. So what do I mean by a closed orientable hyperbolic surface? It's just this guy, right? I mean, you take a genus G surface, bunch of handles attached to a sphere. Okay, and it's hyperbolic, so I'm going to assume that the genus is at least 2. And we all know how to get such a thing. You start with a 4G gon, and you glue its edges according to this diagram. So, for example, you glue A1 to A1, glue B1 to B1, etc. This gives you this surface, and this also immediately gives you the presentation. So the presentation is you have a generator for each one of those edges after gluing. And you have only one relation, and the relation is you have to multiply the commutators of A, AI, BI from 1 to G. Okay, so for example, at the beginning of the talk, I gave you this A, B, C, D. Okay, this would be the pi1 of the surface of genus 2. Okay, good. So now the first thing we're going to do is we're going to take the Schreier-Graph interpretation of stability and translate it into branch covers. Okay, so we're going to see I mean, the issue somehow is we want to take a group theoretical property, then we translated it into something that's combinatorial. Now the next thing is we're going to go into geometry, right? We want to use the fact that it's a hyperbolic surface and use geometry somehow to get the stability. So the way we do it is we use branch covers. So pick some point on sigma. Sigma is my surface. Here. Let's say genus 2 just be. So I pick some point P. And now note that when I take away this point, I get a surface, which is no longer compact, but the pi1 of the surface is exactly the free group on the generators A1 up to Bj. Okay, and the reason, I mean, you can see it in this diagram. If I just take the point in the middle and I just deformation retract everything to the boundary, I just get a graph with 2G edges, right? Rows with 2G edges. So this is just a free group. So far, are we happy? Good. So now, for stability, we're given an almost action, but an almost action is an honest action of the free group, right? So we're given an action of the free group, but every action of the pi1 of the space, of a nice enough space, corresponds to a cover of the space. Okay, so again, we had sigma, we moved by 1 point, this gave us sigma 0, the pi1 of sigma 0 is the free group. Now we're given an action, the action corresponds to a cover. So I have now, this was my surface. I remove the point, I get some cover with a bunch of points missing. Okay. And now the next thing I want to do is I want to just metrically complete omega 0. Okay, so add back the points that I just told you are missing in this picture. So this was omega 0, but now I'm just adding back those points. Also downstairs, and I had the cover of omega 0. Cover of sigma 0, omega 0, and now I get a branched cover. So this is a branched cover. So what's the difference? So note that for every point other than the white ones, the marked ones, a neighborhood of this point would just be mapped to a neighborhood downstairs. So it would be a cover outside those points, right? But when I look at those points, what I see is something like the complex plane being mapped to itself with the map z goes to z to the n. So it just wraps around a bunch of times. Okay, so locally around the points, what I might see is something like should I do it? Maybe let me do the final thing. I have it here. So okay, let me add a small arrow around this point and see what happens upstairs. So upstairs, this arrow might lift into several arrows around the point. Okay, so some points might be just regular, like a neighborhood of this would just look like a neighborhood of this guy. But some points I might see this neighborhood opening up to let's say, 3 copies of itself. Okay, is this clear? What do I mean by a branch covering? Okay. So now let's try and understand how to actually build this omega explicitly, because we'll need to say something about those singular points. So the way I like to think of it is you start with the Shayagaf. So let's maybe try and think, how do you build a cover for omega? Just like an honest cover, not a branch cover. Okay, so you're given an action. From the action, you can construct the Shayagaf. Okay, and now what do you know about this Shayagaf? You know that whenever you follow the path, let's say this path, commutator of A, B, and then commutator of CD, you end up in the same point, right? So just attach to this path the disk, this disk. Okay, so you start with the Shayagaf. Shayagaf of this action. I didn't give it a name, so oops. Okay, and so what I want to say is that I want to say attach a disk. So the disk is going to be the one with the relation A1, B1, A1 inverse, B1 inverse, so on. So attach this disk to every instance of this relation. Is it clear what I mean by that?
Can you just say what you mean by attach here?
So just glue a disk. So okay, I'm looking at the Shayagaf, and I'm looking at the path A1, B1, A1 inverse, B1 inverse, etc. Okay, so if this was really an action of the pi1 of sigma, then those paths would close up. And what I'm asking you to do is take the disk that has this on the boundary and just do it according to this, to the path. And this would give you the cover that corresponds to this action. Okay. Obviously, we're not in this situation because we don't have an action of sigma here. Okay, so what can you do? What can you still do? So what you can do is you can do the following. We said that if you follow this path, reading the relation, maybe you will not return to x, but some power will return to x, right? Just because everything here is finite. So great. So what I want you to do is the following: take the disk and cut along the following arc. Okay, so I have the point that I removed. Okay, so this is my special point P, and I want you to cut along this path. Okay, take your scissors, cut along this. Okay, you open up this disk, and now along the boundary of this thing you see the relation, but it doesn't close up anymore, right? So attach a bunch of them until it closes up. Okay, so if maybe let's call R the relation, the one relation that I have, AIBI. Okay, so I look at my Shayagaf and I'm reading R. Okay, so let me do it more schematically than this, because otherwise I will not be able to try it. So I said if it closes up after one arc, glue a disk. This we understood. Okay, now what happens if it doesn't? So I go along R one time, maybe I need to go another time, maybe a third time. Okay. Let's say this is the situation we have. So what I'm asking you to do is take this cut up disk and attach it here 3 times. So here's one copy of the disk. Right, this is my point. This is going to be the lift of P. And here's another copy of the disk, and here's the third copy of the disk. Is it clear? Yeah? I mean, at this point, we should really understand because we're going to use this a lot. Okay. Great. So now we understood how to explicitly build omega, this branch covered. And now let's try and see.
Nir, just to clarify, the non-continuous lines in your picture really becomes a point, I guess, right?
The dotted lines are what?
The disk, the boundary of the disk is in the one-to-one correspondence with this path, which you denoted R.
Yeah.
Right?
So this point in the downstairs, like in sigma, this point is identified with this. Upstairs, there are different points.
But
is this the?
I just want to make sure to understand completely what you mean by this picture. In the picture you made here, it's like you have 3 disks that you glue.
Yeah. So I cut up this one. I got something that looks like this. I have P in the middle, right? I have the dotted lines, and now they're separated into
the dotted line looks like in this picture, like in the boundary of the disk. But the disk, the boundary of the disk was really fooled by R before, no?
So, okay, when I cut along this arc, I get, I mean, the boundary of the new disk has 2 parts, right? It has the white part, which is the relation, and it has the yellow part, which is going to P and back.
Right, so you kind of cut it and open it. That's exactly what I
thought. You should have, right? After you cut, should get it.
You cut and open it. Okay, good.
Okay.
I have a little question. You cut in any point or at the beginning of the relation?
At the beginning of the relation.
Okay.
Thank you. Okay, so now I have this, like, the disk became like a wedge, right? Or a sector or something. And now I'm just attaching, let's say, 3 of them, or until I have to close up. And this is exactly the branching that happens here. Okay. So maybe the number of such things, let's call it if this was V, let's call it D of V. Okay. This would be like the local degree of this branch cover at V. Okay, so here it's just to be. Okay. Great. So yeah, so now that we have let me say one more thing. If we look at the Riemannian metric that we have on sigma, right? We have some hyperbolic metric on sigma. When we go around P, we see an angle of 2 pi. Right? I mean, when we go around any point, we see an angle of 2 pi. Okay, great. If we just lift this metric upstairs to omega, suddenly we have something that's not a Riemannian metric, because we have those special points where we see the branching and where the angle is. So this is 2 pi, this is another 2 pi, and this is another 2 pi. Okay, so overall the angle around this B would be dV times 2 pi. Okay, so I'm no longer looking at hyperbolic surfaces, but I'm looking at hyperbolic surfaces with cone points. So the cone points have some multiple of 2 pi as the cone angle. Okay?
Nir, can I have just, maybe it's a stupid question, but how do you know that you indeed close a loop here when you go a finite number of times on R, and not just going one time on R to a different vertex and then you get to a stable vertex, and then you you stay at that stable vertex.
It's an action, right?
Oh, okay. So you define
Everything has to be a bijection. I cannot go to somewhere and then lose somehow injectivity. Okay, so now let's observe a few things. So the first thing is what's the area of omega of this branched cover, where the area I'm measuring with the lifted up metric from sigma. What do you think this would be?
Wait, what is omega?
Omega is the branched cover. So if omega is the branch cover of sigma. Hint for the area, I don't care about the extra points that I added, so I can just compute it for omega 0 and sigma 0. Okay, so the question is, how many copies of this disk do I see upstairs?
So that's
So I mean, it's just the cover, right?
yeah. So shouldn't it just be the dimension of the cover?
Yeah, it's just the degree of the cover,
The
exactly.
degree of the cover.
Exactly. So here I have the degree of the cover times the area of sigma. Okay, so for us, I mean, we don't care about what's the actual numbers here, but the only thing we care about is this behaves like n. Okay. So it's proportional to n. Great. Now the more difficult task is what's the sum of all the local degrees of singular points. So singular points are points like this one, where I see more than 2 pi. So this should be, the number of times R didn't close up to didn't close up, right? Every time I see R, I see another 2 pi and another +1 to the D of this vertex.
If you sum over all points and not just singular points, then it should sum up to n.
It should have, yeah, exactly. It should sum up to n. That's true. But if I sum over singular points, I'm actually exactly measuring how much this was far from being an actual action, an actual covering. Okay, so what's the answer? The answer is it's roughly, so I mean it's proportional that we proportional to delta times n, right? Which is the amount of sort of defect that I had in my action. Okay, again, this is the number of points for which the path labeled R doesn't close up. Each one of them gives me +1 to the sum on the left. Okay. So what's the new setting that we have? The new setting is we have a branch covering.
I guess you have to say something that the D of every such vertex is also not too large. And because there are not too many points for which violates the relation, right?
You can do that, but I mean, I'm measuring the total singular degree that I get. So this takes this into account. It could be all concentrated in one vertex, right?
Yeah.
So this one vertex that's very singular and has delta times n of the angle there, degree there. Okay, but it's small. I mean, the overall thing is it's small, and that's exactly the point. I have a huge branch covering, so the area is huge, is n, but the number of singular points there is relatively small. It takes up a small percentage of this surface. Is it clear?
Yeah.
Okay. So now let's go into the strategy of the proof. how do we use this branch covering and we just said to show flexible stability? Okay, so the idea is the following. So we start with the branch covering. So again, I'm denoting it as the surface, and I mark the point P, and maybe I mark some arrow there so that I can count for the singular degree at this point. Okay, so what's the first step? The first step is we want to cut up the surface into pieces that have small boundary. Okay, so the first step is find a graph gamma on omega. This is omega. Okay. Okay, with the length of this graph. So I'm gonna go over this. I want the length of this graph to be small. Okay, so what do I mean by that? So I want a graph, and the graph, let me tell you what are the properties. We're going to see soon how to exactly construct this graph and what are exactly the properties, but the graph should be such that it cuts this branch covering into surfaces that have no singular points. Or maybe, forget about the first step. I just want everyone to be on the same page with me in what we're after, right? We start with the branch covering, and what we're looking for is a covering, right? Stability means I can turn an almost action into an action. Okay, so the whole idea is I want to change few things in this branch covering and end up with an actual covering. Okay, so the idea is the following: you should cut the surface into pieces that have no singular points in them. Okay, and once you have those pieces with no singular points, find a way of making them into a cover. So the first step is you should find a graph gamma on which you're gonna cut your graph, cut your surface. So the graph is gonna have the singular points as vertices. Okay, it's gonna have edges which are geodesic on the surface. Okay, so something like that. So it's gonna be some embedded graph. And the two extra conditions that I want, and those are really the crucial conditions, is that the angle that I see here is less or equal than pi. Okay, so in particular, I don't see something singular. I don't see something that's over 2 pi. I mean, that would be a disaster, right? If I see something that's over 2 pi, there's no way I could embed this into a cover. Okay, but here we'll demand something stronger. We want it to be less or equal than pi. And so this is true for any such, so I should add more edges. So this should be less or equal than pi, so on. Whatever. There should be more edges.
Using the hyperbolic metric everywhere when you say length and so on.
It's all, yeah, exactly. So on sigma, I have a hyperbolic metric, and I lift it to omega to get something that's hyperbolic except for those singular points where I get more angle.
Geodesics or hyperbolic geodesics?
Geodesic or hyperbolic geodesic, yes.
And the point being you want to glue these along the geodesic when you make your new cover?
The point would be I will cut along this gamma.
Yeah.
I'm gonna, so let's just wait.
Maybe
one step at a time. So the first condition, so again, vertices are singular points, edges are geodesic. First, third condition is that the angle would be less or equal than pi. And the fourth condition is that the total length of the whole graph would be small. Okay, so I sum up over all the lengths of all the edges, this should be small. Small meaning smaller than epsilon n, epsilon. Okay, So this is step one. And now the step two is what Peter was asking about. So step two is, first of all, you cut along this thing. So let's do it in the drawing. Cut along gamma.
Is it clear that this is possible to get the length so small?
We'll see. We'll see how to get that. It has to do with, okay. Just let's wait. We'll see everything. So step two is you cut along gamma, and you get a bunch of surfaces, maybe one. I don't know. Okay, so you get a bunch of surfaces. Sorry if, by the way, the degrees of the covers and the genus and all those things do not match.
But they surfaces with boundary, which are geodesics and cone angle less than pi.
Exactly. So they have boundary, and the boundary is sort of locally convex. I have angles here that are less or equal than pi. Okay, so that's the drawing you should have in mind. Okay. So step two would be, given those surfaces, find a way of sort of capping them and making them into a cover. So the surfaces are omega minus gamma. So I want to cap them somehow. So, so I want to cap them, but I don't just want to cap them in whatever way. I want to do it efficiently. So I don't want to add a lot of area when I do that. So if you remember area, so let me go here. Area translates to the number of points, n, okay, on which you act. So adding small area would just mean I enlarge n, so this hence the flexible stability, but I do so in a controlled way. So I'm only going to add epsilon n. Okay, area.
Can I ask a geometric question?
Yeah.
You have this omega, which is a branch cover, and then you're looking for a regular cover. They're both hyperbolic inside with singularities. Are you really asking that the one is Binyamini Shram close to the other, something like that? That is that the one manifold looks like the other one at most locally over bigger and bigger neighborhoods in more and more percentage of the space. Is that really what you're proving?
I think yes. Yes.
It looks like it, yeah.
It's even more than that, because when the Binyamini Shram, the points can be, very anywhere. Here, there is a little area that you add a little piece, and you are different only in that little piece in every one of these pieces. So in particular, it's been in Binyamini Shram, but it's in a kind of in a concrete way, I guess.
Okay, so just to understand what's happening here at the very end, I mean, we did this process, we did it on the branch covering. We have to translate everything back to actions and this interpretation with Schreier graphs and changing a few edges. And the point somehow is that the edges you should change are the edges that sort of cross the blue boundary, right? The edges that cross gamma. So gamma is where things are going to be destroyed. The yellow part that I just added, this part, would be the extra vertices that you'll have to add. And again, the only changes will happen along those edges, which are the edges crossing gamma. Okay, so if the length of gamma is small, it's not hard to see that the number of edges you're changing is small. And that's exactly the stability part of the proof. Is it clear? Where the length.
So it's kind of interesting that you always kind of make the correction into an action which is not transitive on the endpoints. Right? Because once you...
No one claims that the thing would be disconnected. So you could, you cut this graph, but the graph is not necessarily separating, right? I mean, in this picture, I drew something that is separating, but a priori, there's no reason for it to be. So for example, I mean, you actually know such things, right? Because you can choose this omega to be some kind of an expander surface, and then you know that you don't have such a graph cutting it into.
So what is the meaning of the cuts? That in spite of the fact that you cut, what is left is kind of piece. It's an open surface, but maybe still connected. That's what they are telling me. You mean that the picture you made is a little misleading because it gave us two separate, but they can still be connected. I see. Okay, I think I understand now. Okay, I understand what you're saying.
Yes,
so maybe
It's the picture, right? And it's not necessarily separate.
Yeah,
okay.
It's not separating. Okay, I understand.
Should we go into the proofs of the steps? So in step 1, find the graph. Step 2, you have to cap the surfaces. Given the time, I think I'll only do step 1. It's anyway the, I think, more interesting part. So again, what do we want about this graph? So vertices are singular points. I'm just repeating the list of conditions. Vertices are singular points. Edges are geodesic. The angles between adjacent consecutive edges of the graph at the vertex are less or equal than pi. And last condition is that the total length is small relative to the area, where this C delta, you can just think of being an epsilon, it just depends on that. So as delta goes to 0, I want this thing to go to 0. Okay, so where would this thing come from? So the idea is to use what's called the Delaunay graph. So for this, we want to first define what's the Voronoi tessellation. So let me probably remind you what is the Voronoi tessellation, because you probably all saw it in some way or another. So you're given a metric space, but really think of the nicest metric space possible. So Euclidean plane is where usually people do Voronoi tessellation. Hyperbolic plane is also an option. Here we'll have some modification of the hyperbolic plane. It's not exactly the hyperbolic plane where we'll play this game. And so we have a metric space, and we're given a collection of points. Again, nice enough, discrete enough, okay? And now what we can do is, for given a point in this collection, we can define its Voronoi cell, which is just all points x in x, such that it's closer to P than any other point. Okay. So let me do the example that probably saw sometime in your life. So I'm given a bunch of points in the Euclidean plane, and I want, let's say this is my P, and I want to describe the Voronoi cell of P. So I'm looking at all points that are closer to P than to any other point. So for example, this edge, that's exactly the points that are equidistant from P, and this Q is this line. Okay. And the same for this point, for the next point, and the next point, so on. So this is going to be the Voronoi cell of P. Okay. And for every other, so Q, I'll have a Voronoi cell for Q, so on and so on. And this gives me a tessellation of X. Okay, so if the space is nice enough and the points that is nice enough, then I really get a tessellation by polygons, let's say. Okay. So how do we do it in our setting? So what's the space in our setting? The space is the universal cover of omega. So remember, omega has the hyperbolic metric coming from sigma, but it's not really a hyperbolic Riemannian metric. It has those singular points. I mean, even though it's not hyperbolic, it is still locally ket -1 for those who know what that means. So it's still negatively curved. Oops. Negatively curved in the sense of it's locally ket -1, and hence the universal cover is actually ket -1. Okay, and I'm going to take as the collection of points all the con points, all the singular points where I see angle bigger than 2 pi. Okay, and I'll construct the Voronoi tessellation of this collection of points in X. Okay, so far this seems nice, but maybe I should warn you that, I mean, with the exceptions of very nice spaces, the Voronoi tessellation in general is not as nice as you might think. Meaning, for example, the Voronoi cells are not necessarily convex, which is something you would just think happens for, let's say, ket -1 spaces. It doesn't. Okay, so caution. Proceed with caution. In general, even for ket -1 spaces, the cells are not convex. Okay, but here, sorry, yes?
Ket -1 means hyperbolic?
Ket -1 means it's better than hyperbolic. Better than the hyperbolic plane. It's slimmer than the hyperbolic. But whatever, negatively curved. Think of something that's negatively curved where, I mean, in our case, it's really for every point, except for the singular points, you just see a piece of the hyperbolic plane. So really see something that's a surface with -1 sectional curvature. And the con points are even more negatively curved in some sense. Okay, so in general, you should really be careful when you do those Voronoi cells. But here, when we're in a very special situation where we actually chose all of the singular points as the set of points for the Voronoi cells. So in this very specific situation, the Voronoi tessellation is very nice. Okay, meaning all the cells are are convex. They have boundary that's made out of geodesic segments. Okay, so fortunately, V is nice. So, for example, cells are convex and have boundary that's piecewise geodesic. Okay, so we really get a tessellation of X. We have those polygons, so to speak, and they are tessellating our X. And so we can define the Delaunay graph of this tessellation, which I'll just use a shortcut and just say it's the dual to the Voronoi tessellation. Okay, so in the picture we have above, so let me go back to this picture. It would just be this. Note that in this example, somehow I got that all dual edges actually pass through the edge which separates the cells. This doesn't have to happen, but it doesn't matter for us as much. Okay, so the Delaunay graph would be the dual to this, and we actually choose it such that all the edges are geodesic. Okay, so this is going to be our lambda tilde. Lambda tilde is the Delaunay graph of this set of singular points in the universal cover. Okay, but note that I have the action of omega on its universal cover. That's X. Everything that I chose, so P was all the con points and the Delaunay graph and all those things are invariant under this action. Okay, so what I actually get is a graph that's defined downstairs. Okay, so I get this graph lambda. Maybe I should have said, I mean, it's not trivial in general that, for example, the edges of the Delaunay graph do not cross one another. Okay, so I mean, there are things here that just, I don't know, we're lucky and they actually happen in this case. Okay, so we get, whoops. So we get this graph lambda. I have until, I have 15 minutes more, is that correct?
Yes, we go for 75 minutes, including questions, so.
Okay, I see.
Can you just remind what was condition 4?
Yeah, so I'll go over them. Okay, so lambda satisfies, I claim that lambda satisfies 1 up to 3. So 1 was the vertices are singular point. This is just the way we define it. Right? The second condition is edges are geodesic. Again, it's just the way we define it. Third condition is that the angle between two consecutive edges is less or equal than pi. Okay, so why does lambda satisfy this? So given a point, so here is a point P of one of the cone points upstairs, it has angle which is some multiple of 2 pi. Out of this whole angle, which is a multiple of 2 pi, choose a sector that's of angle pi. Okay, here I have some multiple, some huge angle. Okay, and now note that so this whole thing happens in the universal covering X. Okay, but the group acts in such a way that it acts co-compactly on X. So I should see more points in this sort of half space. Okay, and if I see more points there, I'll see more Voronoi cells, and I'll see dual edges to those. Okay, so in particular, the Delaunay graph, say blue, will include at least one edge in this sector. Okay, so every sector of length of angle pi has an edge in it, meaning that the angle between two consecutive edges must be less or equal than pi. Okay? Okay, so good. So it satisfies 1 up to 3. And now I get to your questions, Alex. 4 was the really essential thing, which is the length of gamma is short. Okay, so I just chose to take all the edges somehow. I mean, what I get is probably long, right? There's no reason for it to be short. And here is where we really use something that's really hyperbolic. Okay, and what do we want to do? We want to take out some edges. So we want to take, first of all, redundant edges, meaning edges that do not contribute to condition 3, right? So if I have edges that have, if those two have something that's less or equal than pi, I don't need the middle one, right? Just take it off. That's one idea. Another idea is we don't want to take long edges because we want the length to be short at the end. And here is what we use to do that. So the idea is there is a payoff. If you have a long, if you can only choose long edges, then the Voronoi cell must accumulate a lot of area, and a lot being exponential in the length of the edges. So let me draw the picture for you. So I have the point P. Okay, again, that's one of those con points. and I'm looking at a sector of angle pi around P. And imagine that all the Delaunay edges that I can choose from are extremely long. Okay, so here are all the other cone points on the sides. They're all extremely long. Okay, so this is, let's say, bigger than some huge R. What does it mean about the Voronoi cell? So how do we construct the Voronoi cell? You connect 2 points with a geodesic, take the midpoint, and you draw a perpendicular. This should be the equidistant points, right? So this is sort of the picture you should have in mind. They go half the distance. This is sort of the Voronoi cell. Okay, somewhere. In particular, the Voronoi cell would include some huge ball of radius r/2. Not exactly. So why not exactly? Not exactly because I'm just looking at a cone around P, and I'm asking this to happen in this cone. So it could be potentially that I have points on the other side which are close to P. Okay. But okay, there's still room to play with here. So if they are close, they couldn't be too close. They're all lifts of the same point of sigma. So there is some distance between P and those points. And so the Voronoi cell will be captured somehow between, let's choose another color maybe, something like this. So I look at this region in between. Okay. And its intersection with the orange sector, let's say something like this. So what I'm claiming here is if all the edges you have to choose from are very long, the Voronoi cell will have to include a sector with some fixed angle phi. Okay, phi is some really fixed thing, fixed angle, and radius r/2. Okay, where r is how long the edges must be. And so this thing is, I don't know, you can write the formula. It's this formula. You see, it's sinh, blah, 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 whatever. Some exponential, I mean, doesn't really matter. So it's some function of the length of r. Sorry. This would be the area of the sector. Okay, where this function, I mean, the only thing we'll need in this function is the fact that it's convex and sort of exponential, like, okay, it's sinh squared, if you really want to do the computation. Okay, so now what do? We say remove all points remove all edges that are too long. So too long would be controlled by what's the area of the Voronoi cell intersected with this half space H. Okay, so again, I'm looking at all edges at a point P whose length satisfy this inequality. And the argument that I sort of sketched here very, very briefly is that such exists. Okay, that's the point. Okay, such edges exist. And then the next thing is what I said before, you should just remove redundant edges. So look at the minimal set that satisfies 1 up to 3 inside epsilon prime. Okay. And okay, so now let's do some estimates, very easy estimates. So one estimate is how many edges did we choose? Okay, so note that in any half plane around P, I choose at most 2 edges, right? Because the middle one would be redundant. Okay, so how many edges will I have in total? I have something that's proportional to the total angle I have around singular points. So what's that? That was delta.
Less than 2 times the degree.
It's even better than that because we only look at singular points. Okay, so it's delta times n. This is what we said, the number of singular points, or the total angle around singular points is very small relative to 1. And this is the number of edges you'll need. Okay, now what can we say about the length? Well, we know that any such edge would have to contribute something to the area of the bone. Sorry, is there a question? We have to contribute something to the area of the Voronoi cell. Okay, and when I sum the area of all the Voronoi cells downstairs, I get the area of omega. Okay, so what I get is the sum over all the edges of this function. So this, I could just call it f of LE above. Must be less than, well, maybe I overcount, but not by much. Let's say 4, just to be safe, the area of omega. Again, because each one of them contributes something to the Voronoi cell, or we can just use this formula. And the total area in all the Voronoi cells is just the area in omega. Okay, so that's great. Now let's just use Janssen inequality. So I divide by the number of edges. And I use Janssen, so I know that F was convex. So I can do this. Whatever I have here. This is something like area of omega is something like m. This is something like delta n. It's 1 over delta. Okay, and now look at F inverse and do the computation. This is the length of gamma. So you get that the length of gamma is something like, I mean, let me not be precise, but it's like 1 over delta, where it should be arc sinh something, blah, 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 whatever, F inverse, oops. Times n. And this thing, as we said, this behaves like delta times ln 1 over delta or something like that. Still goes to 0 when delta goes to 0, which is the only thing we care about. Okay, so I mean, this was step 1, and I'm out of time. But I think you got the big picture of what's happening. We cut along this gamma. We have to cap this guy. This is basically some kind of quantitative Lerf property. You want to show that each such surface embeds in a finite cover. Okay, so there's some techniques that have to do with choosing the right presentation and playing with that. Okay, so I think I'll finish there unless you have questions.
Thank you very much. Because we try to be strict and to finish after 75 minutes, let me thank you, but then I will ask you questions. So people who want to go to eat or the local, so thank you very much. So we finish for today. For those who want to leave us, don't feel bad. Next week, we have Lev Glebsky, who will talk about the connection between Sophic and equations in finite groups. So it's a little bit related. And in the month of December, we'll take a turn and we'll go to the other type of stability with respect to unitary matrices. And it will be a little bit more kind of analysis and things like that. Thank you very much. But if you don't mind to stay, Nir, I want to ask you some questions and maybe some others.
Go ahead.
So 2 questions. One, it looks like your method is pretty much effective. Can you say what's the connection between delta and epsilon?
Yeah, it's this number. So it's something like delta ln 1 over delta, basically. I mean, this F inverse is arc sinh, maybe square root of
What's well, that's approximately, it goes like what?
Delta.
It's polynomially, linearly, what is it?
It's this. So this is the epsilon.
So epsilon is more, okay. Epsilon is ln 1 over delta. Okay. Second question. I mean, well, you kind of, on one end, you are heavily use surface theory, so it doesn't look like it will work for 3 manifolds. But at least the Lerfner's property is known now for hyperbolic 3 manifolds. Is there a chance to do anything for? And even for a very concrete one, you know, that we can give you a very concrete presentation like such 3 manifold, which fiber over a surface, and, you know, you can give you a precise presentation.
I mean, that's a great question. The short answer is I don't know, but I think there is, you know, there's a part of this argument that's really surprisingly 2-dimensional. And the part is exactly this kind of picture. So, I mean, what you could imagine is you have let's say a 3 manifold. You can still do the branch covering over, let's say, 1-dimensional things inside, right?
Mm-hmm.
Okay, so you get something that looks like, you know, 3 space with a bunch of 1-dimensional singular fibers there. Now you want to cut this thing, right? So when you cut this thing, you need to introduce 2-dimensional thing, right? Codimension 1. But instead of gamma here was codimension 1, meaning a graph, right? A 1-dimensional. If you're doing the same, if you're playing the same game in dimension 3, you will have to introduce 2-dimensional objects. And immediately you sort of lose this fantastic payoff between long edges and hyperbolic amount of area. Mm-hmm. So I mean, you have surfaces that they also grow hyperbolically as the volume would grow. So maybe that's kind of, this is why I'm thinking, you know, this method might not work for 3-dimensional manifolds, but you should definitely, you know.
I have a related question. Your theorem is really a geometric theorem, which says that if you have a coned hyperbolic orbifold or something with hyperbolic metric with cones, and another one that you can somehow find a map from that, which is an almost isometry, to something which is smooth. So I was wondering if you can't prove this variationally. If you have, rather than all this cutting up and so on, you might think that there's a way of naturally introducing a functional which smooths out the cones at some small expense and gives you the map that you're looking for. It seems it's a purely geometric theorem, firstly, right?
I mean, maybe like this part, because the other part.
Yeah, this part. No, the part from the branch covering, that's straightforward. I agree, but the beef is here. Is
no,
the
I mean,
fact
there's the second part of like actually like capping the surfaces, which is it's
Yeah.
very much, you know, I mean, I don't know
So-
if it's geometric as much as it's like topological. But
Well,
okay.
but it's a question, it reminds me a little bit of the Ehrenpreis problem of finding a quasi-conformal map, which is like in the graph, there's always if you have locally the same, there's a finite common cover, this theorem of Lateman or somebody. And then the Ehrenpreis version, which I think was proved, where you have a quasi-conformal map with small dilatation. It's a bit of that flavor that you are saying, but you're not looking at hyperbolic metrics, you're allowing these other things. The other comment I had is there's a natural moduli for these that is used less, that instead of making cones, you could remove little circles of constant curvature. So in the uniformization theorem, the strongest form of the uniformization theorem is the theorem of Kerber, that you can map a multiply connected domain to a domain bounded by circles, round circles. And there's a moduli space of these attached to that actually Phillips and Osgood and myself studied many years ago in extremizing determinants. And we had to go through a lot of combinatorics like this of coalescing of these punctures. So it's not clear to me, you've succeeded. So I'm not going to argue with you that you went to this cat space and you're comfortable. But there are other geometries that one can associate it with this. And then there seems to be some kind of distortion theorem that you have that you can adjust it. I believe there's a very beautiful geometric theorem that you have proved here. But maybe, I mean, your co-authors would know about that, I'm sure, as well.
Okay. Okay, I'll ask.
Your paper on the archive, maybe I'll take a look and see if I can try to formulate what it is.
It is.
Yes? It's on the archive? Okay.
I'm not sure if it answers your first question, but it's not just a matter of making this smooth. You also need to maintain the property that it covers the original surface because you don't want to lose the...
Yeah,
right, so it's a theorem about coverings, much like Ehrenpreis conjecture was. Yeah. It just seems to me very much a geometric thing, and that's why it's two-dimensional in many ways. But I'm not arguing with success. You've seen your way through. I'm just suggesting that there seems to be a underlying geometric principle here.
I have a question to Alex. Actually, you just mentioned some specific three manifold, which fiber. So you have specific presentation, or?
Yeah, you can write. You can take, say, a surface, a genus surface, and you take semi-direct product with a pseudo-Anasov automorphism. You take a kind of a generic pseudo-Anasov automorphism of pi1 of pi g. Then this semi-direct product is a fundamental group of an hyperbolic manifold. And you can kind of write more or less explicitly a presentation, and I just wonder if anything can be applied to it.
Let me just say one more thing, because I mean, you mentioned sort of the left you have for three manifolds. I mean, it doesn't really give you what you want here, right? Here you want, I mean, you want a very good kind of quantitative left where it's controlled by the boundary of the surface. Like the amount that you add to make it into a finite cover is controlled by the boundary and not just, you know, a multiple of the degree or something like that, which you usually get from most arguments.
Mm-hmm. Well, in a sense, even if it will not, without a quantitative, it will be interesting. There is a notion that we sometimes call, it's not such a good name, very flexible stability, namely that you allow to correct it even with very, very large capital N.
Mm-hmm.
And it will be interesting to know even that property. For many applications, that's enough. So if this can be done, it will be still nice, very nice. Well, okay, we can. Are there any if somebody wants to ask, please just ask. I cannot see you, so please don't wait for me to.
Thanks for the nice lecture. I enjoyed it.
Yeah. Okay, so thank you very much, Nir. Thank you very much, and good night to you over there.